Hello everyone, welcome to our meetup about the optimal solution to exercise 4 of the IBM Quantum Challenge. A couple of weeks ago, we celebrated the anniversary of the IBM Quantum platform, and there was a person, only 4 people all over the world, that got this optimal solution for the most difficult exercise of the 4 exercises in the challenges. And that person happens to be studying a PhD in Spain. His name is Luciano Pereira Valenzuela, and today we have the honor of having him as a guest speaker in our meetup. So thanks a lot, Luciano.
Thanks to you.
Thank you. I'm going to tell you a little bit about the biography of Luciano. He studied a bachelor's and master's degrees in physics at the University of Concepción in Chile, and he's currently studying a doctorate of condensed matter physics, nanoscience, and biophysics at the University Autónoma of Madrid in Spain, under the tutelage of Juan José García Ripoll and Tomás Ramos del Río, both from the IFF-CSIC, the National Center of Scientific Research in Spain, and he's interested in protocols to characterize quantum devices. And today he's going to explain us what is this optimal solution for the 4th exercise of the IBM Quantum Challenge. Thank you, Luciano.
Thanks for the introduction. First I want to start with the context. Okay, the IBM Quantum Challenge was a series of exercises proposed by IBM to celebrate the anniversary of the IBM Q platform, the platform to use the quantum computer developed by IBM. Today I will talk about the solution of one of this exercise. The special is that this was the best solution for this exercise. Okay, so first the challenge. So the challenge was to find an accuracy and efficient implementation of a given unitary transformation. This transformation was a 4 qubits matrices, so it has a size of 16 times 16. Now this is fixed, so it is just only one matrix, and the idea is implement this matrix in a quantum circuit using only U3 operation and control node operation. In the figure, you can see the matrix. On the left, you have the absolute value of the U, and on the right, the phase of each number. Okay. Seeing the colors, you can know that the matrix is very arbitrary. That was the difficult of the problem, but also have a structure because some colors are repeated. So the idea to solve this problem is exploit this structure to find this circuit. Okay. To approve the exercise, the exercise 4, our solution have to satisfy 2 conditions. The first one, this implementation has to have an error less than 0.01, where the error is defined by this distance. Okay. Okay, so it has to be an accurate implementation of the transformation. And the second condition is that the circuit has to minimize as possible the number of operations used. This is quantified by the cost function defined by this equation. So this number are the number of control node gates used, and this number is the number of control U3 used. So you approve the exercise if your cost is lower than 1,600 points around. Okay. Here we have we can construct our circuit with two gates, U3 gates and control node. The U3 gate is a 1-qubit gate defined by this equation here. So it has triangles that are free parameters that we can choose to produce any operation of 1 qubit, and in our circuit are represented by pink boxes. Those are the angles. So this is our first ingredient to construct our circuit, 1-qubit gates. And the second one are the control node gate, that is a 2-qubit operation. So it can generate entanglement between the qubits. So this is defined by this equation. And in the circuit is represented by this blue line with these dots. Okay. Well, the control node has 1 qubit target and another that is the control. Right. That's it. Control and target. So if the control is in a 0 state, the second qubit remains equal, and if the first qubit is in state 1, the second qubit are negated with the NOT gate. See? Yes? So now I will talk about the algorithm I follow to construct my solution. So it is based in the following proposition. So consider an unitary matrix U and a set of operations L and R, such as satisfies this equation. So here is the U matrix, and the operations N and R are multiplying from both sides, and this product is equal to the identity. So if we found operations such as fulfill this equation, we have the following decomposition of U. Okay, that's very simple. It's just invert the operation in the first equation, and we get the second one. So the problem is reduced to try to find or construct the operations L and R. So a convenient way to choose this operation is trying to diagonalize the matrix. Okay, so this protocol I followed has an iterative structure. So I first apply one operation, try to diagonalize a bit, then apply another, and continuously diagonalizing the matrix. I take this idea from this article. I have read this article years ago. It's about interferometers. It's a very similar problem. It's implement a universal multipole in interferometers using only 2x2 beam splitters. It's very similar to our problem in quantum circuit. So in this figure, the crosses are the beam splitters. So with this, these are iterations. In the second iteration, this replay allows us to construct this zero on the matrix. That can be initially arbitrary. Then use on the other two beam splitter to produce other two zeros, and repeat until we have a diagonal operation. And this interferometer produce the wanted unitary operation. Actually, with this protocol, you can also prove the universality of the control node and U3 gates. But if I follow the same algorithm, the number of operations grows quadratically with the number of qubits. Okay, so I try to make something similar, but exploiting the tensor product structure of the space, because we have local qubits. So it's a system very different to this one that the beam splitter acts on two rows or two columns of the matrix. In our case, we have blocks matrices. So I try to block diagonalize one qubit in order to continually, again, iteratively, diagonalize the matrix. So here I define a block diagonal matrix that has this form. Okay. Here, A and B are arbitrary operation of the remaining qubit. So the idea of my protocol is use the UTKs to try to block diagonalize the operation, okay? In order to find the matrices L and R to construct later the unitary matrix. If we are in the case where A and B are different matrix, we have to use a control operation to decouple the qubit. Okay, this is the second part important. So we have first try to block diagonalize the matrix with U3 gates, and then when we have the block diagonal matrix, trying to decouple the qubits with a controlled operation. Okay, when we are in this step, we can reduce the size of the problem because here we have an identity, here another matrix, where. So we can omit this qubit, we can remove and just work with this matrix. So that's why we reduce the size of our problem. And then repeat the same procedure until you have 1 qubit or 2 qubit, because 2 qubit gate is very easy. This kind of protocol is also not very new. Similar protocol had been used in tensor network, for example. So this is not a very novel protocol for solve this problem. Okay, now I start to solve our problem. So remember that we have a fixed unitary matrix. Yeah, okay, this one. This is this one. So we have to try to explode the structure of the matrix to try to block diagonalize it. So we look in the matrix, we can see that it has the following block structure. This block is equal to this one, and this one is equal to this one, and the phase is the same. Okay, so this matrix can be rewritten in this form. So this is the main diagonal block are equal, and then are also equal. So it has this structure. Here we define A and B, so with these blocks. So to block diagonalize this matrix, we can remember that the identity and the NOT gate can be diagonalized using Hadamard operations. So we can rewrite the last unitary in this form, where now we factorize in both sides a Hadamard gate. Okay, and in the middle we have actually a block diagonal. Here is the identity, here is a C gate defined with this way. So this is a block diagonal matrix. In the circuit, this matrix C in this form. So the blue are the Hadamards, okay, in the qubit 3. And in the middle there is a big unitary between all the qubits. Now we choose the operation LRR in order to block diagonalize the matrix. So we have to invert this operation and this operation, and choosing L and R with this U3 operation that implement actually the Hadamard, we obtain this matrix. Fine, so we have a block diagonal matrix. We're defining A and B for convenience. We are now in this problem. So we can check that now the blocks are different. That is the second step, are different the blocks. So we have to use a controlled operation. Yeah. And noticing that the matrices B and A are related by this equation, you can write U as this one, or equivalently in a matrix form, this one. Okay, so the red matrix is a U3 operation on the qubit 3. The blue matrix is a control node operation between the qubit 1 and 3, or 3 and 1. The qubit 3 is the control. And the purple matrix is the remaining. Actually it's just a full diagonalized matrix on the qubit 3 because the two blocks are equal. So in the circuit, see in this form. Okay, so choosing again conveniently the operations with this the control node and the U3 corresponding phases, if we diagonalize the qubit tree. So in the graphic we can see that now the blocks are actually equal, and the another blocks, the non-diagonal blocks are 0. You see, the purple or maybe the blue is 0. It's not good. So this is the idea of the protocol. Here we can now reduce the size of the problem, removing the qubit tree, redefining the matrix U3 as just A sub 1. We have now this problem. So this is now an easier problem. So we have just repeat the same procedure to the next qubit. So in this case, we going quickly, choosing these operations, we again full diagonalize the next qubit, the qubit 2. In this case, we have to use a Control-C operation. It's different to a control node operation, but can be applied using a control node and 2 Hadamard with this circuit. So we can use it in our circuit. Yeah. And then reduce again the size of the problem to only 2 qubits. And again, choosing these operations, we actually got the identity. You see, the purple is 0 and the yellow is 1. So this is an identity. So good. This is the goal. What's our goal? So we have found a decomposition of U in this way. So with this matrix, we can construct their corresponding circuit. This one. And checking the solution, we can see that the error is very near to 0. This is because this algorithm search for exact circuit, an exact decomposition of the matrix. So it's not very surprising that this is very near to 0. And its cost is just 54. It's very good because the upper bound of the cost was 1,600. So it's a very big difference. But we can reduce more the secret because we can join the U3 operations that are, for example, this and this. We can join them because they are together, and there is not a control node between them. So we can join in. Reduce the number of control tree uses. This decreased the cost from 54 to just 50. Very good. I was very happy in this moment, and without loss precision. So in this step, to try to reduce more the circuit, we have to use identities. I employ the following identity that I saw from the quantum computation and quantum information of Nielsen and Schwan. Thank you to them. This property is to change the target and the control of a control node operation using 4 Hadamards. So you see 4 Hadamard here. You can turn the control and the operation of the gate. So for example, in our circuit we have many Hadamards. For example, we have in this control node we have this is a Hadamard, this is a Hadamard, this is a Hadamard. So adding 2 Hadamard here because it's inverse. Yes, you can add 2 Hadamard, put 2 Hadamard here. You can use the 4 Hadamards and use the property and change the control and the target. So from 3 U3s, you reduce to just 1. So you have 3 less. And you can apply the same property in this control node and this control node. It's very easy, just seeing the matrices that have a Hadamard near, for example, this. here, this hammer. So we obtained this final solution. Okay, that was my final solution. Checking the error and the cost, we have a near zero error and a cost of 45. A cost of 45 is an implementation of you using only 4 control nodes and 5 U3 gates. That is a very good solution because we start with a circuit that has a very big size. And the funny thing is, it was actually even better than the solution found by the developer of the challenge. They thought that the best solution was 46. So I was very happy, but this just show how difficult is this problem. It's very difficult to know when you are in an optimal implementation of a given unitary matrix. Okay. Asier Adams he loved my circuit and made the following animation. So the bars are the qubits, the blue lines are the control node, and these pink things are the control 3 gates with their corresponding angles. Okay. Many thanks to him. If you want more information about this animation, he wrote an article about this on a web page called Medium, so you can find it. To finish, I would like to end with a reflection. In 1943, Thomas Watson, this guy, that was the president of IBM, said, "I think there is a world market for maybe 5 computers." In those years, the first computer were being designed. Was the first was the born of the computer science, and this phrase just showed that he never thought about the great impact that the computer will have on our society. This represents the potential of the science and in particular, the potential of the quantum computer. The quantum computer can generate a technological revolution. So I invite all of you to research or continue researching in quantum computing. Learn Qiskit is very easy, very easy. And maybe participate in the following quantum challenge. Thanks for your attention. Yeah.
Okay, thank you so much, Luciano. It was an amazing presentation. And okay, I see that Julian, you were trying to go unmute too, right? Okay, sorry. I wasn't sure if you
know who was going to
if you were speaking. No. I will leave it to you.
So now we only have one question in the chat, and it's by Javier González Conde, and he's asking, "Hi, I would like to know how did you obtain the control operation that turns the diagonal block matrix into 2 equals blocks? Thank you."
Okay, in my case, I obtained all the operation just seeing the matrices. So I try to see the absolute value and try to see the phases. So for example, just seeing the phases, I want to come back to that. For example, here, this equation, I obtained it just seeing the matrix. Seeing the phase between B and A, I obtain this number, and then seeing the blocks, the block structure, I noticed that they are like a permutations or are intercambiable. And actually it's a control operation between them. So It's just seeing the matrix. Just seeing the matrix. That is. Yeah. Another question?
No, and we don't have more questions, so I think that's everything.
Yeah. Thanks for the invitation, and also thanks to IBM to create this challenge. It was very funny.
Okay, so thank you everyone for coming here, and this talk will be uploaded to our YouTube channel, so you'll be able to find it in our channel in a few hours. And yeah, thank you very much.
Thank you. Clap, 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 clap.